Welcome to week 9. Can I get someone to tell me in the chat, am I coming in loud and clear? Let me know if you can hear me out there. Smash that chat button. Hello, Sichuan, Jitao, Sabrina, Jia Hong, hello, hello. Week 8. It is week 8. I just asked a poll on who's finished the writing assignment, and about 26 people have said yes, 5 people have said no. Nobody has said what's the writing assignment. So I hope it's going okay for you. I hope it's going okay. All right, today's tutorial is a tutor-led tutorial, and what I'd like to sort of talk with you about today is inverse functions. So this is mostly chapter 6 from the set of problems. Okay, there is also chapter 7 to look at, but I think I'll look at that in a different tutorial. Okay, so you might want to watch this one and then watch another one where we talk about chapter 7. That way it's sort of self-contained. Okay, well, let me share my screen with you, and I'll have a look at some of the problems that we're going to discuss today. So here's the PDF. This is just the problems for chapter 6. And I thought we could talk about question 2. Okay, so here you've got 2 functions, and you're asked to, find the inverse functions associated with those things. Okay, so let's start with part A. Suppose you've got a function 3x plus 1 defined on the whole real line. What is the inverse of that function? Okay, so part of this question is about finding how you can actually calculate the inverse of a function, and then what it looks like geometrically. All right, Brian, if the advice Brian's asked in the chat, sir, I have a question. Is there any example of how the written assignment should look like? Have a look at the printed notes, Brian, the course pack. That's an example of how the typesetting should look. Does that make sense, Brian? Because they're usually pretty careful and pretty well set out. I mean, look at what's on the screen at the moment, right? That would satisfy all of the 5 criteria, hopefully. And that's the best advice I can give everybody for their writing assignment. Check your work against the 5 criteria on Moodle. So, Brian, does that help? So there are lots of examples in your course pack. Yeah? Brian, hello, are you there? Yeah, just have a look at the course pack. So this is page 127 in the course pack. Okay? All right, so let's have a look at question 2. Okay, so for part A, let me share my document camera with you. And we can get started. Okay, all right, so inverse functions. Remember, inverse functions, they sort of undo, let me darken that down a bit. Yeah, they undo the original function. So here, a function is defined by 3x plus 1, and we're going to okay, Brian, can I suggest if you want to ask those sort of questions, the Choose Your Own Adventure tutorial might be better for you. Does that make, because there's a choose your own adventure tutorial right on now, on right now. So it might be better if you just go and jump into the choose your own adventure tutorial. Okay, hope that's helpful. So here's our function, and we are considering the function defined on the whole real line. And the question is, what is the inverse? Okay. So we don't need to actually draw anything, but it's helpful to make drawings sometimes. So let's actually find out what the actual inverse function of this is. All right. So then we can draw a picture. So I'm going to introduce some notation. And the strategy is to make x the subject. So you want to rearrange this and kind of make y a function of x. So 3x is going to be y minus 1. And so x is just y minus 1 over 3. Now, once we've got that far, we can sort of relabel things and let f inverse x be this right-hand side with y replaced with x. So I'm going to replace that y with x. Okay, so now let's actually check to make sure this really is the inverse of that. Okay, so we're pretty sure that this is correct, but let's do a quick check just to make sure that we understand the inverse. Okay, so we want to check that the inverse, when applied to the function, just gives us x. So this acting on this just basically that they undo each other. Okay, so let's take f of x and put it in there. So we'll replace x here with 3x plus 1. Okay, so that's obviously going to disappear and the 3's will cancel. So that's good. We like the look of that. And let's do it the other way. We want to go up here and replace x with this. Okay, so the 3's are going to cancel out and so will the 1's. So that's enough. Okay, so we're happy with that. All right. So pretty easy. Let's have a look at the sketches of these two things. Now, did somebody say GeoGebra? Let me share my GeoGebra screen with you and we can do some really, I mean, these are simple graphs, but let me just show you. All right, so here is our original function, yeah? So I just zoom out a bit. Here is our inverse function. You can see I've just used the invert command here. GeoGebra is not great at finding inverse functions, but it can do it sometimes. And what you'll see is if we put in the line y equals x, then there's this nice reflection between the green function, which is the original function, and the blue function, which is the inverse. Okay, and that holds true for the graphs of all functions and their inverses. They're generally reflected in the line y equals x. Okay, so that's a nice test to see whether or not your inverse function really is the inverse. Okay, so that's really helpful from a geometric point of view. Okay, All right, so, yep, so that's enough for that question. Let's do part B. So part B, if I can share that with you again on my PDF. So you can draw those by hand on the same diagram. I'm not going to do that, but it's up to you. Okay, so part B, the function g is defined by x squared plus 1, but x is less than or equal to 0. Okay, write down the domain and the range of the inverse function and find a formula for it, and then compute the derivative. Okay. All right, there's a good question in the chat by Ling Tang. Hi. So is inverse of a function just mean making y the subject and replace y with x at the end? Look, that's part of the process in finding inverse functions. Okay. Like if you wanted to talk about sine inverse, right? That's not going to work. Okay, because it's hard to flip these things around. But as a process, that it's fine. So moving the things around is more about a process, but it won't work all the time. I hope that's helpful, Ling. Now, Zi Tao, what is R? R is just a real number line. Okay, so this is just negative infinity to positive infinity. Okay. It's just a set of real numbers, C tau. Okay? All right. So what's the domain and range of the inverse and what's the formula for it? Find the derivative. Okay, so part B. So let me share my screen via the document camera. Okay, so consider, yeah, we'll call it G. So this is going to be defined by x squared plus 1 for x less than or equal to 0. Okay? All right, they want us to find the domain and the range of the inverse function. Okay, so an interesting concept here is that if this, let's say this function is a one-to-one function, right? The inverse then always exists. So let's draw a little picture here, see if we can find the domain and the range of this function on this interval, and then we can work out the domain and the range for the inverse. Okay, so let me just draw a quick sketch. So it's a parabola and it sort of looks like that. Yeah? Okay. So who can tell me in the chat what is the range of this function? Who can tell me in week 8 what is the range of this function? Who can tell me? Jiao, Yanlei, Andy, Jitao, yes, Sichuan, Taoran, Fad, thank you. So you can see this is always above, greater than or equal to 1, right? And the domain is sort of already fixed, okay? So the domain of G is, let me get a better pen, is this interval here, and the range of G is 1 off to infinity. Okay, now this is clearly a one-to-one function, right? Because if I draw any horizontal line it's going to touch the graph at most once. That's a quick test to see whether you've got a one-to-one function or not. Okay, so our G is one-to-one on this interval here. And so the inverse exists. All right. So why did we calculate domain and range? Well, we just swapped them for the inverse. This will be the range and this will be the domain. Okay. So we're just going to split these over. The domain of the inverse is going to be this. And the range of the inverse function is going to be, oh, hang on, did I make a mistake there? Oh, sorry, I made a mistake. Okay, so the domain is going to be this. Yeah, and the range is going to be this. Whoops. Okay. Phew. Xinyi, you got your hand up. Were you about to point out my error there? Oh, hang on. Yeah, that's correct. That's correct. Okay. So the last part of this question asks you to find a formula for the inverse. Okay. So we've sort of swapped those over. Let's see if we can actually use this to compute the inverse. So Xinyi Shen, I can see your hand is up. Do you have a question? If so, just put it in the chat. I'm just going to lower your hand. Okay. All right. So can we sort of rearrange this and find the inverse? Okay. So let's consider y equals x squared plus 1. And we're assuming here that the x is less than or equal to 0. All right, that's going to be important in a minute. Okay, because that's actually the restriction that we started with. Yeah. Okay. So now let's try to move this around and make x the subject. Yeah. So if I take the square root of both sides, we're not sure whether we want the positive square root or the negative square root. So can anyone tell me, if I take the square roots here, do I want positive or negative values? Can anyone tell me in the chat? Positive or negative values? Okay. A couple of people not sure. Some people positive, some people negative. Yeah, we worked out the range earlier. Right. So this, even here, it just tells you, right? Yeah, we do want the negative. Yep. So why? Because we know x is less than or equal to 0. Okay, so now let's do what we did in the previous question and define the inverse to be this function just with y replaced by x. Okay. Yep. Okay. Last part of the question, they want us to compute the derivative of, oh, hang on, did I put f there? Oh, I should put g there just to be consistent. Okay, I had g and g inverse there, so I should be consistent there. All right, last part of the question, compute the derivative. So let's just differentiate that and we can finish off the question. All right, so in order to differentiate this, you can do it a few different ways. One way is using the chain rule. The other way is just, basically think of this as a power, bring the half to the front, bring the derivative of what's in the brackets to the front, and decrease the power by 1. So it turns out to be something like this. Okay. So there you have it. Okay. So let me just try something here in the background on GeoGebra. Okay. Let me see if this works. So just bear with me for a second. Yeah, if you draw a picture, you'll also see that so I won't do it in GeoGebra, but if you see here, you kind of know what's going to happen, right? You're going to have, I've got a red pen. Yep. Here's your line. You're going to get a reflection in the line y equals x there to get your inverse function. Okay. All right. Okay, let's have a look at another question. Oh, yeah. So let's have a look at question 3, and I'll share my PDF with you. Okay, so question 3, one-to-one functions. Now, oops. Oh. So here's how you define a one-to-one function, and it's very easy to test geometrically. You just draw horizontal lines, and you know a function's one-to-one if those horizontal lines touch at most once. Okay, so back to the questions. All right, so here we are. Right, question 3. Show that this function has an inverse function whose domain is the whole of the real line. Okay, so for that, let's share my document camera. All right, there we are. And our function is this polynomial equation. And we're asked to show that this has an inverse. All right, that's basically what they're asking us to do. Show us that there's an inverse function, and the inverse function is defined on the whole of the real line. Okay. So let's use GeoGebra here, and we can make a picture of this function. So let me just pop something in here. All right. So let me share again. All right. Here is the function x cubed plus 3x plus 1. Okay. So who can tell me, is that function a one-to-one function? If I zoom out, it's still, yes, it is. Thank you. Thanks, everyone. And it looks like it's a one-to-one function because if I draw any horizontal line, it touches the graph at most once, right? Now, this function, it's also an increasing function from left to right. So every increasing function is a one-to-one function and therefore must have an inverse, okay? So that's what we're going to do with this question. We're going to show that this function has a graph that is increasing. All right. So let's consider the derivative of our function. It's a nice friendly function. It's a polynomial, so they're nice to work with. So we differentiate this, we're going to get 3x squared plus 3. Okay. And let's, I don't know, we can factor that if we want to. But you can see here, this is positive and this is positive. So this is going to be positive for all x on the real line. So what can we say? That we've got a function whose derivative is positive, therefore the function must be increasing. On this set or this real line. And so f is 1-to-1. This is my way of writing 1-to-1. Thus, f must have an inverse function. On this. Okay? Oh, Fard, that's an excellent question. Fard's come in the chat. Is it the same if the function is decreasing? Can anyone help Fard out in the chat? Is his idea correct? Is it true? Yes or no? Who can have a look at Fard's question in the chat? Jia Hong says yes. And you're absolutely correct. So even though this is an increasing function, if we had the decreasing function, then the conclusion would be the same. Okay? Why? Because a decreasing function is also one-to-one and therefore has an inverse. Okay? An inverse function. Great question. Yeah. Great question, Far. Thank you, Jia Hong. Okay. Let's move on. All right, question 5. Okay, let me share my PDF back with you. All right, question 5. Suppose that a function is this polynomial now. So this is a bit different to the previous polynomial. It's still a quadratic, but instead of plus, we have minus 3x. Show that f is not a one-to-one function on this set. And then find all the intervals where f does have an inverse. Okay, so that's what this question is basically asking you. Okay, so before we start, let's look again at, have I done GeoGebra? Yeah, I can do GeoGebra again. Okay, so let's go to GeoGebra and see what's going on here. Oh, sorry. Okay, So that was our previous function. Now let's make a small change. Bam. Okay. So we've made a small change. Now, is this function one-to-one? Well, no, it's not, because if I draw a horizontal line, say if I draw, I don't know, the line y equals 1. Oh no, hang on. Let me write that. Let's j equals 1. Let's try that. It's not liking what I'm doing. If I consider this horizontal line, it cuts once, twice, and 3 times. Okay, so this obviously isn't a one-to-one function everywhere, but what we can do, we can slice it up into 3 parts where the function is one-to-one. Okay, so the function is one-to-one sort of to the left of -1, between -1 and +1, and then from +1 to the right. Okay, so there's 3 places where this function is one-to-one. But on the whole of the number line, the x-axis, it's not one-to-one, right? Because the horizontal line test fails. Okay, so if I was doing this question, I would just write that the horizontal line test fails here, right? So this is question 5. So let's consider the following function. So it is x cubed minus 3x plus 1. Okay, and the first part of the question says show that this is not a one-to-one function. So our f is not one-to-one on the whole of the real number line because it fails the horizontal line test. So what that means is if you can find a horizontal line that touches the curve at 2 or more places, then it's not one-to-one. Okay. For example, y equals 1 touches the curve 3 times. Okay. Andy's got a good question here. We have to draw the graph before we conclude that, right? Well, yeah, I would draw it. I've just used GeoGebra to help me. But yeah, I think it's very powerful. Or you can just choose a value, 2 values of x that give you the same value of f of x. Okay, that's basically what the horizontal line test is doing, right? So let me just look at Andy's question for a second, right? So I'll just go back to my GeoGebra. So you can see, say here, if x equals 1, if x equals 0, you'll get a value of 1. If x equals, whatever's down here, you'll also get the function equals 1, and same over here. Okay, so sometimes you can just do that algebraically, but drawing a picture can help a lot. Okay, hope that helps, Andy. Okay, so let's continue. Okay. Part B in this question asks you to find all the possible intervals. Okay. And so it's not too difficult from our graph, right? Let me go back to the graph. Okay, so you can see there's a turning point at -1 and at +1. So they're going to be the end parts of our three intervals. So from negative infinity up to -1, that's going to be one interval. And then from -1 to +1, that's another interval. And then +1 up to infinity is going to be our third interval. Okay. Now, if you want to do this using calculus, let's see how we would do that. We would just find the turning points via differentiation. So the derivative of our function is going to be 3x squared minus 3. So our turning points are going to occur at x equals plus or minus 1. Okay. So our three intervals where f is 1 to 1 are, well, it's going to be negative infinity up to +1, and then, -1, and then -1 up to +1, and then 1 off to infinity. All right. Okay, and lastly, what is the domain of each of the corresponding inverse functions? Okay, so now it gets a little bit tricky. So we have to look at the range of each of these little parts of the curve. So let's go back to the picture. You can see why GeoGebra is really helpful now, right? Okay. So who can tell me in the chat, what is the range of this function for x less than or equal to -1? Who can tell me what is the range of our function? What is the range of that blue function? Lucas, yeah, absolutely. I would put the negative infinity before the 3, but yes, you're absolutely right. And then you can see here it goes from -1 to +3, and then -1 off to infinity. All right, Andy's got a good question. We have to draw the graph before we conclude that, right? Sorry, we are supposed to draw this graph without computer software. Well, in your final exam, you will have Maple, Andy. So, I would be pretty relaxed about drawing these graphs. Does that make sense? Yeah, so sometimes people freak out and they go, I can't draw that by hand. But actually, in this course, because you have access to Maple, it's actually pretty easy, right? So let's go back to the document camera. So this is the corresponding domains, and then the corresponding ranges. Okay, so between there and there, we worked out it to be negative infinity to 3. And on this interval, it was between -1 and +3. And then it was -1 to positive infinity. Okay, these are going to be the respective domains for your inverse function. Okay, so phew, it's a lot of work. Okay, probably because you need to split things up. All right. All right, everyone. I'll do maybe one or two more. Let me know how things are going in the chat. These are pretty simple questions, but it's good to draw a picture, and it's good to just understand what we mean by an inverse function. What are the strategies to calculate an inverse function, and what do they look like when we plot a function and its inverse and the inverse function? Okay. All right. So let's go to question 10 now. So I'll share my PDF. So much sharing going on. I really need those hotkeys so I can share quickly. All right. Question 10. This is now combining calculus with inverse functions, okay? So how do we compute the derivative of the inverse of cos? Now, this part B might look familiar to you, but part A is probably less familiar. Okay, so let's work out what our strategies are for this particular problem. Okay. Now, one of the key ideas here is implicit differentiation. Okay, so that's one of the really key strategies for this kind of problem. All right, so this is question 10A. So we want to show that the derivative of the inverse of cosine is this function here. Now remember, the inverse of cosine is only defined for certain values of x. Okay, and if you look in your course pack, you'll see that there's a big table there of functions and their inverses. Okay, so one of the strategies here when you're solving this problem is what I like to do anyway, is to simplify this, rearrange it, and then use implicit differentiation. Okay? So I'm going to differentiate both sides with respect to x. And here, obviously, y is a function of x. So I can simplify this using implicit differentiation and the chain rule. Okay, so obviously this right-hand side is easy. It's going to be 1. Now over here, I can introduce the chain rule and then differentiate with respect to y. So you can see what I've done there. You can think of these dy's as cancelling out, yeah? Okay, so that's the same as d dx. What it means is I can now differentiate this, right? If I differentiate cosine y with respect to y, I'm going to get negative sine. So I'm going to have dy dx times negative sine y equals 1. And so what I'm trying to do here is get this dy dx on its own because y equals cosine x. So that's exactly what I want here. So I can divide here, but what I would like is to get my answer in terms of x. Okay, so we just need to do a little bit of algebraic manipulation now. So sine y is here, x equals cosine y. So what is the relationship between sine y and cosine y? Well, I can write it like this. Right here, I've just basically used sine squared plus cosine squared equals 1. And what is this? Well, cosine y equals x. So now I can get back to that x. Okay, which is exactly what we wanted to solve. So let's call this star. Okay, so you can see that, first of all, we sort of simplified the notation, moved things around, and then used implicit differentiation or the chain rule, whatever you want to call it. Finally, we had to get back to what we started with. So we wanted to get from this y expression back to something involving x. And a lot of these questions are the same. If you did part B for this question, which is the derivative of tan inverse, it would be very similar, and you'd just be using something like sec squared equals 1 plus tan squared or something here. Okay. All right, last question. Here's one that I've done from my private stash. So let me see if I can find it. Yeah. So where are we? I'm just looking on the PDF now. So just give me a second. 14. Okay, so let me go to my PDF. Okay. So 14 is labeled as a H or a hard question, but with GeoGebra, it's pretty easy, right? Draw the graph of cosec x, or 1 on sine of x. Show that if you just restrict x values here, then it does have an inverse function. Okay, so let me do the first part of this. I've only got a couple of minutes, but here's one that I've done in GeoGebra. Hang on, let me just bring that up. There we go. Okay, so let's clear that. And here's the cosec x function. And I've just restricted it, as you can probably see, for x between 0 and pi on 2. Okay, and you can see here that this function is 1-to-1. It is a 1-to-1 function on that x interval. Okay, what does that tell you? Well, it tells you that it has an inverse, right? So what does the inverse look like? Well, I'm glad you asked. How did I get that? Well, GeoGebra could do it, but it can't always do it. So how do you know where the graph is going to be? Well, it's the same old idea. You can sketch that part. Here's the line y equals x, and you've just got this line of symmetry, right? You reflect it through this line. Okay. Now, let's say I just put in Let's take that away for a second. Let's say I just put in, I don't know, this. So this is, if I'm just considering that graph for all x, you can see that that is clearly not a one-to-one function, because if I draw a horizontal line, it's going to touch at many points, right? More than one point. So that's why this has been restricted to this interval, because it is one-to-one, right? So just let me show you again. There's the inverse, and there's the line y equals x. And you've got that lovely, lovely symmetry, okay? All right. So that's always a good check, whether you're using pen and paper or you're using some sort of software. It's always a good check to put in the line y equals x and look for that symmetry. Okay, folks, that is the tutorial done and dusted from me and Quokka. We will see you next week. Good luck with the assignment if you haven't finished. And yeah, just keep going. Only a couple of weeks left in term. So I'm looking forward to spending the next 2 weeks with you. Thanks again. Namaste. Enjoy the day. And we'll see you later.